Hi everyone, and thanks for coming today. So basically, thanks for the Jane for the nice introductions, and I'm happy to share some of our recent works in OOD detections, and hopefully this will be a joyful discussion there. So feel free to interrupt me in the middle if you have any kind of questions, and happy to answer that. So before we move into the main content of today's talk, basically I will do a quick like the introductions of where I'm from. So basically I've stayed in UQ for 7 years, and UQ is located in Brisbane, so very near to like the central area, like to Sydney and Melbourne, and the whole Australia is basically a big zoo. Have a lot of interesting animals like the quokka, kangaroos, and koalas. So, well, very interesting. We are actually the down under of the whole globe. So we are actually enjoying the summer at the same time. So you will see like the people wearing Santa Clauses doing surfing during the Christmas seasons. So the UQ, we have a big data science disciplines, but I'm actually growing a small research group focusing on the generalization issues in 2D and 3D things. So our lab, we have 1 postdoc there and 7 PhD students. So what we are doing currently is addressing the domain shifts. So across different topics, including like domain adaptations, like the specifically test time ones, and transferability assessment to check which checkpoints is more generalizable and could be better used for your downstream tasks, and also considering for the label shifts on like for the open set and OOD detections, and also understanding what's novel in your test data. So open vocabulary or open word alerting. And also interested in how to curate informative and helpful training data to help the model generalize. So learning to select, including using active learning and dataset distillations. And for applications, we do a lot of things surrounding the autonomous drivings, including like the camera, LiDAR-based, and multimodal, this kind of hybrid BUV detections. And also we are currently moving towards to the end-to-end autonomous driving frameworks. So basically we have perceptions and planning, and we combine all together, but the planning will be our ultimate goals that will drive towards for us to carefully design how do we do the perception modules. So those applications will be a really good test beds for considering the domain shifts and also the robustness. So due to the time limits, probably we won't go through like the 3D vision works, but focusing on the particular the label shifts like for the OOD detections. So I basically go through to our recent works for the general OOD detections and 1 application to the object detections, and we'll see what's the main differences and some unique challenges there. So we like to start with like a real world applications or the case study. So my thesis students and we were working on a small project, very interesting one with like with the city council stuff. They're interested in developing camera-based solutions to find out all different kinds of defects along the whole full path and caravan channels. So to identify those kind of different types of cracks and also potholes, we are running through this like a small course in trying to summarize all these kind of the road conditions into a dashboard. And I think it's very common for a lot of like the vision models, they will make a lot of mistakes. Like we notice that if it goes through like the unseen context, or encounters on unknown objects, like the leaves or debris like along the road, it will mistakenly pick up those things as one of our target defects. And this generalization issues, what we refer to, is actually very common and a lot of applications, including for autonomous driving. So you may know this kind of news, a series of like the hazards already happening there, like the Tesla cars on the autopilot modes crashing into the private jets because these kind of things were present like during the training data. So it won't know this kind of white lawn truck is basically one of the objects that will putting everyone in trouble. So how to address it like responsibly during the test run is our focus. So a common solution, or I think it's widely used one in the industry, is like if we want the better generalization, we basically need a bigger model, like the getting more layers stacked and getting wider like the model designs. Well, this kind of recipes and also requires to getting more data. But as you know, like we are kind of getting in troubles is like we soon or later will run out of the data because we only have the internet and everyone is using the agents to generating the data and we are running out of the real data. So as this curve that you can see here, if we want to train the models like with more compute resources for training more epochs, actually we just need more data. Even without any filtering, it's gonna getting better. So if we do not have this kind of resources, we cannot afford to get a more like generalizable model. So this is kind of a disappointing fact that we need to facing now. So to address kind of the data efficiency issues, because we don't want to blindly use all of them, we don't want to like to consume a better generalizations at the sacrifice of like the wasting more resources or data. We are kind of considering if there's a way that we can find a way to quantify like the generalization to with kind of the indicators. If we can find them, then basically we know we are at a good point, or we can just use limited data and carefully select them to train your model and get a better generalization performance. And secondly, if we have these kind of indicators, then we can basically guide our data selections at the very beginning. And we know those data will be useful for your downstream tasks, and we will just use them and get rid of like the kind of a redundant or less useful ones. So for generalization indicators, I think it's a long-standing issue, and no matter it's an application or theoretical works, we have a lot of things that like view these kind of problems from different angles. So including like very classical generalization theories, like the VC dimension-based ones that characterizing, okay, if you're testing data and you're training data, you know what's the discrepancy there. So basically your generalization errors can be bounded, although it's a loose one, but we somehow get the point of knowing how much data we need or how complex the model we probably need to looking for to get a rough idea. But this kind of series is not really working for the deeper models. As you may see, like it suggests like if you get a more complex models, then you probably get a looser upper bounds. But this is sometimes it's not true if you got the large pre-trained models, and usually you're getting the better generalization performance. So the other researchers look at these issues from other points, like from the model's predictions, like from the model logics. If we measure the calibration error is low, like the EC is low, and sometimes it will also reflects, okay, the model is generalizable. And also from the optimization angles for the model flatness, for the loss flatness, and also for some specific model architectures like the over parameterized models with the NTK solutions. And also probably we can just look at the sample sensitivities, like using the memorization scores to characterize how generalizable your kind of model is. So we have a lot of options here, but we just want to show one example, like if how this kind of idea can help us to save your training data and getting better generation. So it's a very like the classical ones developed by the Ben Davies that if you're doing domain adaptation, I guess is kind of the most commonly used ones and a lot of theoretical works. So if you want to categorize like the your target errors, it's actually bounded by your source error plus the discrepancy between your source and target data. So what this kind of tells us is like we probably, if we having a good training data that kind of mimicking your target data, mimicking your downstream target samples, and if you train your model on it, and you definitely get a better performance. So this can be reused like to in return to guide us to find out what kind of the raw data we need to ask the annotators to getting more labels. So in the active learning procedure, as shown on the left side, here you can see like basically giving you unlabeled pool, so millions of raw point clouds, and we're kind of curious about developing a good active learning policies to selecting some particular point clouds and ask them to label that so that we can retrain the model and getting this loop until we run out of our labeling budgets. So this idea, it becomes the critical, how do we design this policy? So the policy can be just a view as approximation of if we can get our selected samples to having the same approximately same distribution of your labels or features or some geometric properties like the density of the point clouds, and probably that is the data you're looking for. So here involves like the hierarchical samplings to get a better efficiencies, and also we have like the Monte Carlo dropouts to getting like the useful gradients for selecting the samples, and also the greedy search to have the same like a uniform distribution for balancing the sparse and dense point clouds. So this is kind of the ideas. And in the later follow-up works that we realize if we just are doing this because it's 2 heuristics, we have 3 different criteria to kind of matching with our target samples. But probably we can just using 1 criteria that will be enough to kind of quantifying the gap between your training data and your testing data. Although we don't have any access to the testing data, so basically we make some assumptions about what we have during the test. So for a more unified criteria, what we're looking for is like for the like we resort to the information theories like the coding rate. I think it's very commonly used for feature selections and also in constructive learning. But here we want to say, okay, this could be a good criteria or a metrics to reflect what kind of information embedded in your training data, and that's kind of important for your output. So here, what's important in the calculation is the covariance. So basically, it's the covariance matrix is d times d. So measuring how similar along different dimensions, and we can just focus on those non-redundant and unique features to select. So if we just basically change these covariance metrics to a kernel matrix, and we can easily adapt it to a sample selection problem. So here the covariance metrics to be replaced by the kernel ones, and we have a bunch of like the different options for the kernels that we can choose. So basically the only requirements is like the kernels should be like the PSD ones, and it has n times n dimensions. So we have different like the choices, like including the linear kernels, the most basic ones, and the non-linear ones like the Laplace RBF kernels. And also we try out the empirical NTK kernels to quantify how your latent changes will affect the next layer's outputs in the gradient space. And this can also kind of measuring the similarity among your samples, and this can tell us to selecting meaningful samples. And just a very quick results is like for the commonly used KD dataset, if you want to do 3D detections in only 3% of the raw point clouds needed to reach the full like the performance trained with the full training datasets. So that's a basic idea here. So getting back to what we start is like, if we want to kind of achieve this kind of generalization, and the most important thing is how do we quantify the gap between your training and testing data, as we just basically tried in the previous works. So assuming that we are following the correct shift assumptions, is we don't need to consider the concept shifts, like so if you got the same x, then you're gonna get in the same y. So we don't consider this kind of conditional shifts. Now we only focusing on, okay, we measure the gap on your raw input side, like the x, and the gap on the y side. So in your raw data size is basically, you can just imagine as a marginal distribution difference. So it could be resulted by your synthetic data to testing on the real data, or a clean data trained on clean data to a noisy data. So this kind of a gap will result in the input biases. And also for some procedures like your pre-processing, as we already did in the previous works, like if we select a subset for your training, and this will also cause the gap between your training and test things. And sometimes when you deploy your models with different sensors or different environments, then also will cause the domain shift issues.
Hello, may I ask a question?
Yeah.
Last slides. Do the marginal distribution have the same support? So maybe there are some support in the training domain does not maybe exist in the test domain. Is it included in your scenario?
Yes, I think so. So a lot of like the domain adaptation works, they have different assumptions here. So I think in the classical ones, they do have these kind of assumptions. Otherwise, they cannot derive kind of the statistical divergence, or to minimize these kind of things. But I think for adversarial learning or other things, they're trying to address that in a min-max scan. So this could be does not considered or rigorously I think proved in those kind of works.
Okay, I see. So you mean they are mapped in a more general space, and
yes. So there's no theoretical guarantee for this kind of works to reach the convergence or.
Okay. So you also mentioned about you capture the divergence in the label space, in the Y space. How do you capture that?
Sorry.
In the Y space.
Yeah. I think for the next slide.
Oh,
so
okay.
Yeah. So another kind of gap is like usually like if you deploy to an open world scenarios, you never assume that those concepts will definitely like already presented in your training data. So that's how the Tesla caused like the getting into troubles. So for this kind of a wide, like the shifts, although we're usually saying like the training concepts will be the subset of your testing concepts. So to safely remove those irrelevant concepts, and what we're gonna do is usually resort to open set or OOD detections. So we're gonna remove those unseen or irrelevant classes so that the models will not classify into those kind of the concepts that we are not interested in. And for open word and open vocabulary, as what we did in the ECCV works is like we're trying to understand what's novel there. So with like the pre-trained VOMs and although it's in the 2D domains, we kind of want to lifting these zero shot capacities into the 3D words by using the projections and also the several rounds of self-trainings that we can achieve these open vocabulary capacities. So I guess I will start with the first, like the OOD detection works. So this is like what we just introduced, like if we only cares about like the label shifts in the target domains. So if we encounter some of the samples that out of our vocabulary, out of our training concepts, what should we do and how can we just basically separate them? And this work that we have done, like for the iClear 2024 is focusing on the post hoc OOD. So OOD has a lot of different variants and definitions. So it could be the training based OOD, like we learn to separate those novel concepts, but the whole post hoc one is the branch of method that focuses on after training. So we just during the inference time, we're trying to find the metrics and basically separate them during the inference. So to mathematically define these kind of problems is like what we need is an efficient scoring function S that we can kind of mimic the behavior of the ID density functions, the PX, so that we can basically using one threshold to separate what could be regarded as like the ID, what will be the OOD. So that's the very simple definitions here. To help, but the main questions or the main challenge in this kind of works is how do we design the scoring functions? Because it's always hard to estimate the ID density functions. What can only do is like basically make some prior assumptions, like, yeah.
In your previous slide, so I want to understand a little bit what's happening. For instance, you have this example, like you train on CFAR10, like a standard model, and then you can use to identify some unknown classes or something. How does it happen?
So it's like now we have a testing data like the CFAR 100. So it has some classes like which shared with the CFAR 10, and we call it as a ID data. And there are 90, the rest of the classes will be OODs, and we don't want to need to classify them because our model is not trained in that way. So if we could safely like reject those novel samples at the very beginning, then we can make sure our classifier won't make this kind of mistakes.
And then for that purpose, you need a scoring function, but it's not yet clear how to create that function, right?
Yeah. So there are a lot of options for designing the scoring functions, and that's the main focus for this book. So but to simply define as we previously introduced, is like the scoring function is aiming to capture what we have for the ID data. So here's some just to clarify some of the common assumptions that we put here as a uniform class assumption, we don't consider like the class imbalance, like the class imbalance situations. But although it can work on that, but our approach does not like putting these kind of things into scenarios. And also, so by breaking into the class conditional the density function, so we can express into very general form. Is on the top we have the partition functions, and on the bottom part we have the basically a partition function for normalizations. So just the two parts to be clear. And usually for this kind of scoring functions or the ID density that we were looking for, we have a lot of OOD methods, like the post hoc OOD methods, including the logic-based, distance-based, and density-based methods. So most of the work relies on like basically looking at what we have in the last layer, the predictions, the logics. So what they want to have is, okay, a very intuitive understanding here is if you're those kind of unknown samples, you never seen that before. So the confidence is definitely lower than the ID data. So this could be a simple separations by just looking at the softmax scores, or what they call is for the maximum softmax scores. And so if you plot a distribution here, is like for ID samples, usually this tends to have very high MSP here, like 0.9 or something. But for OOD, some of them are confused like with ID ones, but most of them tends to have a much lower MSP scores. And other kind of the variance in these kind of logic-based methods, they use the NH functions, the basically logs on the exp of your logics, and plus considering the temperature here, using this free energy score as a scoring functions to separate the ID and OOD data. And all good. So, and some of the books look at the middle, like in the latent layers. So they extract the different features to forming the cluster. So basically they want to using the distance as a scoring functions to separate the ID and OOD data. So if you have already had like the ID samples and easy to cluster based on different classes, and those centered will provide you a kind of a idea of, okay, those will be ID data, they group together, and any of the test data, then we basically calculate Euclidean distance or like this work, Mahalanobis distance, then we could know if you are in the middle, like far away, all of those kind of centers, and you are considering as OOD. So those kind of distance-based methods. And what we can observe here is like those distance functions, it's a good density functions, but it's not normalized. So it cannot be considering as positively like proportional to the density formats that we previously constructed. And the third one is like the density-based OOD. Finally, we're back to what we define here is the scoring function is supposed to be like following the density function that like what we define, what is OOD, what is ID. So, but you know, it's very hard to do because density estimation is always a long-standing issues, especially for the high-dimensional data. So you have to make assumption there to fit or estimating the density for your given data. So what they choose is a typical choices here is the Gaussian. So to fit in that, it looks like it somehow can fit in to the density that we're looking for, but the questions or the problem that it has is it cannot fail. It cannot handle the non-Gaussian distribution if your data is more complex than that. So here, this figure just to show why the density-based works is better than the logic-based or the distance-based. The other figure I didn't show here, but the idea is like, okay, if you just look at this toy example here, and assuming that your density, your ID density follow in this way, and the logics that you have basically will give you false negative and false positive excesses going. If it's out of range, then you will definitely getting a much higher like the logics or MSP scores that you should have. So those will be the false positive and false negative that we need to handle. So if you can fit in the density ways, and those can show better for those kind of extreme cases. So we're back to, we have go through some of the related work in OD and the scoring function designs. But now we want to have a more unified frameworks that we can guide the future, because it's definitely never to be optimal. So we want to find the better way to design the G theta. And also we want to having a tractable estimations without pursuing, like it has to be the Gaussian. So we want to have just a one step more beyond the Gaussian distributions to extend to an exponential family of distribution. So basically it has much more choices that we could consider, like the gamma and a lot of things beyond the Gaussian ones. However, if we just want to directly fit into with your ID data to get the estimation, is intractable and computationally costly. So we want to find a more efficient way to, and this is a support that we can rely on, is called the dual theorem. So if we assume that the psi and phi are conjugate functions, and we can actually converting our problem of seeking the good exponential family distribution into finding basically a conjugate pair of functions that we can do this kind of searching for your given data sets. So I will show what does this mean here. And here in the middle, the D phi here is the Bregman divergence. And why we choose these theorems, that is because like it can basically unify what we already presented in the previous works, that the choices of the square Euclidean distance, the KO distance, and the Mahalanobis distance, those commonly used distance is actually being unified in the Bregman divergence. So just the different choices of your convex functions. So basically what we want to present it here is like the psi and phi, we just, they just need to follow the rules to be the conjugate pairs, but they could be anything. They could be any functions. But to be, to simplify the searching process, and we choose the psi here to be the LP norm because it has nice properties as its conjugate pair is the LQ norm. So now the searching problem, it becomes to, we just giving your ID data, we just need to find what will be a good, the P norm for your data sets. And then we can basically generalize beyond the Gaussian distribution for your scoring function design. So here, what you can see here is like if we replace the LP norm with like with the psi with LP norm, and what we're gonna have is for your Bregman divergence of the D phi can be just replaced with LQ norm. So it's very natural to have this expression here. So now, assuming that we are now fixing the the top, like the partition function problem. And for normalization, we just basically tried 3 different ways to do that. It's like self-normalization, we don't care about, if we don't care about the normalizations, or we use KDE, or we use important sampling-based approximation for your normalization. And it shows like the important sampling usually tends to be a better choice among different data sets. And this is a result that we want to show. So if the Q equals to 2, that will downgrade to the Gaussian assumption. As you can see, like for the CIFAR test beds, the L2 norm is not the optimal choices, and we always have a better ones in the middle in this kind of a searching problems. And we also tested like against the other different, like the NH-based, logic-based, and also the distance-based KN, and the most recent ones actually based on the neuron. And we can show that this searching is computationally efficient and also can achieve better performance across different datasets. So I guess that's the first works I presented. And any questions?
Yes, I have a question. Is back to the last slides.
Yep.
Is there the distance space is measured by NTK, maybe because you are using very deep neural networks? The distance.
The distance one, I think here, I think the related work just use the Mahalanobis, like they extract the latent features like from the ResNet. They didn't use like the NTK in those works.
Oh, okay, I see. Thank you.
So you're learning. So you're learning like probability distribution over the latent space, right? And then you have to design then this conjugate functions, or so you have to learn this parameterization of this probability distribution. Is that correct?
Sorry, learn which part?
So in this case, like when you have to do the out of distribution detection, so what are you optimizing over? What is it that you're like learning here?
So the only parameter we are learning or searching is for the P or Q, but the Q is basically determined by the P. So given your ID data, and we are kind of finding some other OOD data sets, and then we can basically try different choices of P. Then we substitute into the D5 here, then back to this, then we can get the scoring function.
So, and then you say that P is equal to 2 corresponds to the Gaussian distribution.
Yeah.
So it's as if you're then just fitting like a Gaussian distribution to your
so
the impulse, right?
The downgrades to the GM score.
But if it's like something else, then can it be multimodal, for instance?
Yes. Yeah. So because we are basically searching for the exponential family of distribution, so it could be other distribution.
Okay.
Yeah.
Okay, thanks.
Okay. Yeah. So so we just tried the OOD works in object detections, and actually the challenges here is varies a little bit more. It's like in the classification, you only need to know like which one to be kept or should be thrown away. But here in object detection, what's matters is like sometimes you're gonna missing them if you have an OOD. Sometimes you capture them and we say, okay, that's false positive, and sometimes basically the model will ignoring them. So in our nearest works, we're trying to find a way by using the VLNs to capture as much as we can. Then we have a lot of bounding box there. Then we now basically move towards to a classification problem. So if the whole idea is like, we only need to train a small set of learnable prompts for the Grandino, and we're trying to ask the models to capture all of the bounding box or all the objects that present for the given image, and so that we can basically cropping that, and we know it should be OOD or the known classes you're looking for.
Okay, I have a question.
Yep.
So the prompt here is just a discrete input of text, or just some softmax, some new net inputs of.
So it's just some learnable embedding. So
so embeddings in the model itself.
Yeah.
Oh, okay. I see.
So after the tokenizers.
Oh, okay. I see. Thank you.
And yeah, so what we're trying to do is like, if we can separate this problem into two stages. So one will be the class agnostic object detection, capturing all of the objects that we have. Then we can easily do the OOD or open vocabulary for the downstream things. So easy idea is like, we can ask Grandino whatever the concept we're looking for. So we can give them some very generic descriptions like objects, or just basically an adjective of generic, or we can enumerate like the high level, like just like the ImageNet, they use a WordNet hierarchy to go through all of those concepts and ask a Grandino to capture all of instances. But actually, the kind of the issues that we found is like, if you have like presented all of those, you concatenating all of this like the query text all together, and you find out this is what we call the query merging. So if you concatenate all of these query words together, it has a big performance drop compared to if we do for multiple paths, for asking for objects or asking for animals and merging them together. So why is causing that? I think what we infer here is like, okay, if we have a query text that's actually separate a lot, like the plates and the cup. So those are two different concepts. And if we concatenating those two texts together, actually the model is doing fine. But if those concepts are too similar to each other, then the model get confused and the confidence decrease, and that's why the bounding box disappears. So what we're trying to do is we want to grow a variable length of prompts that actually can be separated well, so no overlap between them, so that they can have like to capture all of the instances just in one pass of the inference. And so what we're gonna do is we're starting with a parent prompt, then we gradually grow the child prompts until we reach our termination criteria. So initialization of the child prompt is basically because we assume it's on the hypersphere, so we do normalization. And we basically rotate for the different child prompts for initializations. And then what we're gonna do is train with those kind of two dispersion losses to forcing the child and parent to have some connections while keeping them very separate in latent space by using the negative ones. So the question is like two here is, one is like which prompt to split, and the second is when to stop. So to choose like the most uncertain prompts, that we will counting how many times they basically used during the inference, and we will choose the most frequent ones because they are regarded uncertain and has too broad meanings compared to others. And regarding when to stop growing the learnable prompts, it's like we're gonna checking the maximum angular coverage for all of the prompts that we have. If it reach a too wide angle, that means it captures too many semantics there, and we should stop. So as you can see, for different rounds of the prompt growth, the growths, the MAC is like consistently increasing, and you will see for the prompts that for the child prompts, they're kind of having the smaller angles compared to the upper level prompts. And we also compare that on the COCO and LVS, and it shows like the better performance than segment anything. And we only need one pass of inference to achieve a good results. And this is actually some of the visualization of what kind of instances we comprehensively captured. And also we show some of the data sets they're even missing for different instances. And that's kind of the bottleneck for our experiments. And we also do the downstream OOD detections based on all the bounding box that we have. And we show that compared to the existing works of OOD detections, we're doing much better no matter for known and unknowns in this kind of computation. So I guess I'm a bit behind the time. So quickly a wrap up or takeaway message is like we are, I guess, still far away from the real generalizations. And we're trying to still find out way of better use our existing trained data and forming a better meaningful subsets for pursuing the real generalization. So some of the solution could be resort to using stable diffusion, but sadly it's still worse than the real data. And also in the autonomous driving, you see even with the nerve and 3D Gaussian splitting, those samples look like the real cause, but the model cannot detect them. So it's still a lot of things that we haven't solved yet. And for efficiency, we are kind of moving towards test and adaptations. And this is a survey that we recently wrote that kind of summarized and compared for a small batch of the data. And we show very different trends of what they reported in the original papers. And we are still towards like finding out the modality gap of 2D and 3D and to achieve the real generalization in two kind of dimensions. Yeah, I guess that's all for today's talks, and thanks so much for attending today, and any questions I'm really happy to take. Thank you.
Okay, let me ask one more question. Yes, that's the last slides. So what do you think is the main challenge of lifting the image to the 3D models in the test time adaptation problem?
Okay, that's a tricky one. So we realize like it's not easy to live. It's because like for 2D, naturally you're gonna have a lot of things missing. You only can capture what's present in the front, like for the ego vehicles. So you cannot guessing what's behind it. But the 3D, like the LiDAR, they have more informations of the whole geometry for the global thing. So if you're lifting that, sometimes it's sensor differences, sometimes because of this, like the missing information that will cause a gap of even for generalization.
Okay, I see. Okay, thank you again.